And Maji will tell us about the geometry of secure computation.
So I'm audible if everyone can hear. So thank you, Yuval. So today I will be talking about secure multi-party computation. In particular, how geometry can help us perform secure multi-party computation. So to establish this connection with geometry, we actually came up with something, a new perspective on how security manifests in interactive protocols. Based on this connection, we have been able to motivate new research problems in geometry, in particular real algebraic geometry. And finally, and most fascinatingly, we can actually find physical processes in nature where secure multi-party computations exist naturally without any notion of security. So first thing I must remind you, this talk is in the context of information theoretic cryptography. So everyone has a p-space oracle. Okay. Every function that you can compute efficiently can be efficiently inverted. There is no one-way function, no public key encryption, no OT or beyond. Okay. In some sense, in the context of this workshop, this is the most minimal assumption that you can come up with. And we will tell you how to do meaningful cryptography in this model. So I will present results from a couple of our papers, one that was published last year, one currently under submission. And I will actually cover several results that are currently we are proving in our ongoing projects. So Sogato is my colleague from Maths department, and Hamid and Hai are my graduate students. Hai recently graduated. He's in the postdoc market. Very strong candidate. Please, you can consider. Okay. So in this workshop, I do not need to motivate secure multi-party computation, but let me just give a couple of sentences. Secure multi-party computation is a premier technology that is expected to bridge the data utility and privacy chasm. And it does so, it helps parties compute securely over their data. It outputs only the intended output and reveals no additional information. And it does so by leveraging several resources like computational resources, network resources, randomness resources, and cryptographic resources. And these additional resources create overheads, which in fact are the bottlenecks to its adoption. So a natural question here is to how to minimize these overheads. And we want to perform secure multi-party computation with minimal overhead. So what to expect in this talk? We will be talking about round and communication complexity of secure multi-party computation. So given a task, we'll and a bound on resources like round complexity or a communication complexity, we will show how we can compute that task within those resources, or I will give you a proof that it cannot be performed securely in those resources. So our solution strategy is a new geometric approach, and we introduce a new the new concept of generalized convex hulls to establish this connection. A very interesting consequence of our work is that now we have systematized the space of all secure computation protocol. So we can let loose a computer to find the most optimal solution for us. The way I like to put it is we are no longer limited by human ingenuity and creativity in designing secure protocols. A computer can solve it for us.
And write the paper afterwards.
And the second thing I wanted to emphasize is that I highlighted that I can give a proof that, let's say there is no 5-bit secure protocol for a functionality. This is a lower bound, information complexity lower bound. Traditionally, people come up with, very smart people come up with very slick invariants, and then they prove that, hey, 5-bit protocols cannot satisfy that. We have automated it. It is as simple as testing whether a point lies in a set or not. Okay. me remind again. This is a topic about information theoretic cryptography. Okay, two-party secure computation in the information theoretic plane model. Parties have access to p-space oracles. Okay. So the first part of the talk is completely geometric. Okay, I'll just talk about geometry. And towards the end, I will warn you before I introduce security. And that too will work only with one representative example. Okay, so before I introduce our notion of generalized hull, let me give a new perspective on how we see convex hulls. So let's define an initial set of points on the plane S0. I will define a geometric action that allows us to do the following. Given any 2 points PQ in the old set, it allows me to add the line segment joining PQ to the new set. Okay, so let us assume S0 is our old set, and we apply this geometric action on this old set to create the new set. Observe that I did not insist PQ to be distinct. You can assume P equal to Q. In this particular case, the line segment joining PQ is the point P itself. So what it implies is that old set can be copied into the new set. If you now consider distinct PQ, let's say you consider these two as PQ, then you join this line in the new set. So red points are the points which showed up for the first time in the new set. Black points represent points that were already there in the old set and were copied to the new set. Is everyone okay with this representation and color coding? Everything is fine? Okay. Everyone agrees? Yeah. Huh? Yes. You can choose both and you can write it over it again. And everyone agrees that we could not have added any more points to S1. Okay. So now we apply the same geometric action again on S1. S1 is our new old set. And the new set, first of all, we can copy everything. And observe that anything in the interior of the triangles are red. Okay. Any questions about this?
Please specify the dimension.
It is on the plane. Very good question. If this point was up, you would have had a tetrahedron at this place. Yes.
So just to be clear, when you say 2 points, so initially we just had 4 points, so it was.
Yeah, you have infinite points.
Here, yes.
You pick your favorite 2 PQ and keep doing it. And
so you can. This is how you define it.
Yeah, it's different.
Okay. I'm not actually going to do that.
Let me state it in this way: that apply the geometric action iteratively twice to S0, you will get S2.
So that one action is basically adding all the
old to new. The new
one action you add all the levels.
Yes. Yes. Any questions at this point? Red points are fine, right?
Have like more space, but it's
yes.
to be like this thing ends, but you have like more space. So
sorry.
Like this thing ends there, like but you have like more space.
Yeah. So, okay. So S3, note that everything is black. There is no red points. There are no new points that show up. Once no new points show up, they can never show up. So our objective is to study the evolution of this set under this geometric action. And what we can show is that it stabilizes. And when it stabilizes, it is a convex hull of the or initial point set. Is this okay? But how do we prove that it stabilizes? When does it stabilize? Okay. So towards that objective, there is a very powerful theorem, Carathéodory's theorem, that says that if your initial point set lies in an ambient dimension of dimension D, ambient space of dimension D, then any point inside the convex hull is a convex linear combination of at most D plus 1 points. Huh? Ambient space means if in 3 dimension, if your points were on a hyperplane, ambient space is 2. Okay. So very simple observation. Every point in S0 is a combination of 1 point in S0. Every point in S1 is a combination of at most 2 points in S0. Every point in Si is a convex linear combination of at most 2 to the power I points. Therefore, this must stabilize by at the log d plus 1th round. Okay, so this is how we see convex hull. Any questions, any doubts at this point? Yes.
It tells you that basically you can write everything as a convex combination of the dimension, regardless of the number of points, right?
Yes, that's a very good observation, that the answer is independent of the size of the initial point set, S0. It only depends on the dimension of the ambient space. Very good. Okay, so now let me define what's generalized convex hull. Let's start with the same initial point set. However, our geometric action looks similar, but it allows us to join the line segment PQ and add it to the new set if and only if the points are axis aligned. That is, either their first coordinates are same or second coordinates are same. Is this okay? So again, we can choose P equal to Q, and in that case, I can still add the old point set to the new point set. No problem with that. And now note that the only new line that I can join is by choosing P equal to these P to Q. If I choose this P and this Q, they are not axis aligned. So that line cannot be added to the new set. Is this okay? Make sense? Okay. Again, we can copy over old set to the new set, and we can add this new line. We can copy over the new set. Line. We can copy over the new set, and now everything gets added here. Does it stabilize? Okay, I have run out of space. That's a very good guess. Yes, right? So it stabilizes. You can show that the round where it stabilizes does not depend on the ambient dimension. It depends on how many points are there in the. It may depend on how many points are there in the initial point set.
Start with points, what's called general position. That's it.
Oh, very good question. I was about to. That was my quiz question. Suppose points are in general position. This is my S0. Can you tell me what is the S1? It's the same set because there is no one. Good. All of us aced the quiz. Is this amazing? Okay. Okay. So what are the research questions in geometry? Given S0, succinct description of the set Si, and determine if at all this sequence stabilizes. Okay. Natural questions? Yes.
After finite, can you always prove this stability?
That's the open research question. Just open. Yes. In 2 dimensions, I can prove that it stabilizes in finite steps. Please wait in the last slide for something additional.
Okay, I was just wondering, like, having trouble visualizing counterexamples where it doesn't already do it.
Let me put it this way. This is an open problem in mathematics. That subject is over 3,000 years old.
Very classic.
Very classic. Okay. So I promised that this problem opens up a wormhole that connects research in information complexity with geometry research. So here is the translation to you. Given a functionality, is there a 5-bit protocol for that functionality that translates into a membership query? I can design a query point which depends on the task, and you have to answer whether it belongs in the set S5 or not.
So a task is like a function? Like
yes, a functionality. I will define this more formally. S0, I will define that. It will depend on the task. Okay. S0 subscript task, you will apply the geometric action 5 times to get S. Very good question.
So, wait, so there's Q task and S0 task?
Q means query point, and it depends on the task. That's what I wanted to. secure computation.
No, but what is S0, right? There's two things. There's, you want to ask what
S0 substrate task.
Q-task is
Q-task is a query point and it depends on the task itself.
right, but S0 task
Also depends on the task.
So why is it not written on the slide?
I did not write it. That's a short. Okay. I just wanted to highlight that this is a membership question.
I don't know.
So the question is, the geometric action will not change.
Yeah.
Only the S0 set. If there is a 5-bit protocol, I would like to design it, right? We need to construct the path tree, basically, of the generative story, how this point came into being in set S5. From that, we can reconstruct the secure protocol. If no, then I need to prove or convince someone that there is no 5-bit protocol. This is typically very challenging to do. All I need to do here is to show that the task, this query point, is outside the set. Yes.
But this can be done.
Yes. This is what we showed that this set is not wild, it is stable. There is bound on its algebraic complexity.
So intuitively, it's like the geometric action indicates like the mechanisms of randomizing communication.
Let's wait.
So you don't care about communication complexity and things like that, round complexity? Oh, there is BB. Okay, BB.
bit means
Communication complexity is fine. B.
And that's like Alice speaks, Bob speaks.
No. Alice can speak 2 consecutive rounds if needed.
So you don't care about rounds, only.
Oh no, I can. This problem also translates to round complexity. The geometric action is slightly more complicated. That's why I did not introduce.
How do you define S0?
I will show that. I'll show that.
Okay.
I'll show that with an example. I'll show that. Yes.
Super basic question about the geometric action. When you're moving to the next S, does it need to match up on with the two points that you're connecting? Do they need to match up exactly one axis, or do they need to match up on everyone but one?
This is a very good question.
Just trying to visualize.
So in general, they have to match on first, let's say, a first part of the our ambient dimension being very high dimension space. First few must match, or second few must match. This kind of thing. It will be a linear map instead of a linear function. Okay, I wanted to go to the last one. Typically, we in communication complexity, if there is no security, Alice can send her input to Bob, right? And Bob can perform the computation on behalf of both and send back the answer. So the communication complexity of this is bounded by the size of the input-output domains of the task. It has nothing to do with how complicated the task is. Can we show such a bound here in security as well? This translates into showing that this sequence stabilizes.
this is the communication complexity. The insecure communication complexity?
No, this is secure communication
Oh,
complexity.
secure.
The analog of it will be to show that this sequence stabilizes in some finite number of steps. Okay. So let me establish some connections. So this is connected to a notion of convex hull known as relative convex hull. It is slightly similar to something known as geodesic convex hull, but it is not that. Okay, I want to specify that this is relative convex hull, and it is parameterized by a surface. Oh, you have a question? It is parameterized by a surface C. Let me define the surface C. Pick a point on the plane X and Y, lift it up to height Z, that is the product of the two coordinates XY. So this gives us a curved hypersurface. We can lift our point set S0 to this curved hypersurface, and the new geometric action says that you can join the 2 points PQ if and only if the line segment joining PQ is contained on the curved hypersurface C. Okay. Fascinatingly, for this particular choice of C, 2 points, the line segment lies on the hypersurface if and only if they are axis aligned. Okay. So for you can consider general C. For this particular C, the notion of relative convex hull coincides with what we are studying. Okay. And most interestingly, this is something that we came to know very recently. Folks in partial differential equation, they motivated a new notion of convex hull known as lamination convex hull. This is parameterized by a set lambda. So you are given an initial set of points, and you can join the line segment joining PQ to the new set if and only if P minus Q is in the set lambda. Okay. And they are interested in how this set evolves. And they pose this as a new research problem in algebraic geometry. If you fix lambda to be the x union of x and the y axis, then you can only join points to the set if and only if their axes are aligned. So now secure computation protocols manifest as solutions of natural processes. You do not need a computer to define security or anything. It exists in nature. So the way I like to look at it, like whatever we did in our work, someone smarter can come and prove something better. Our proof will be superseded by theirs, but this connection will stay. Okay. Any questions at this point? Then I will switch to slide crypto.
So yeah, maybe we talk about how do you embed?
Yeah, with an example.
So what do you mean by access align?
The first P1, P subscript 1 equal to Q subscript 1, because they have the same x-axis.
Okay, okay. I see axis aligned. I heard axis aligned. Sorry, my bad. No, that's
Does it go beyond like 2 dimensions?
Yeah,
What's the goal? You need like a plane aligned, or we still need axis aligned?
I will explain the generalizations.
So much does it connect to what you said before, or just
this is it. I'm not going to say anything more about geometry part is finished.
no this connection
Oh, how it connects back to here?
no between one of those this is the one you defined before. Yeah, okay.
I'm not going to talk any more about any of these things. Geometry part is over. We are going to
No, but does it help us, this connection between incompressible Purdue, whatever,
Yeah.
to convex? Does it help us to understand better communication complexity, or just nice observation or beautiful observation that is not really?
I will look very clear.
Okay.
It's just a nice part. I do not see how far it moves.
You said, I didn't see security parameter anywhere. We're talking about perfect security? Okay.
For this.
Yeah, just.
Yeah, it will become very clear. Okay, so now we are back to studying cryptography. We'll study a problem at the intersection of information complexity and cryptography. We want to understand the communication complexity of secure computation. The model is very simple. We have two parties, Alice and Bob. Alice has an input, little x. Bob has an input, little y. And their objective is to sample an input z that both agree on according to a probability distribution fxy. So I want to highlight fxy is a probability distribution over a sample space. Okay. It can be deterministic. It may be randomized. Okay. And we are considering honest but curious adversaries, the simplest and most elementary model. And the question is there a b-bit secure protocol for the function f? All the distributions f of little x, little y are public knowledge. Everyone knows the task that they want to perform. Okay. What was known before? If the output is determined by the inputs x and y, then I will say that the function is deterministic. This is the seminal result of Chor-Kushilevitz-Beaver, where they characterized all deterministic functions that have two-party secure computation protocols. And since 1989, this problem was open, the characterization for randomized case. Okay. And the non-triviality is to deal with both inputs and randomized output. If you do not have a randomization, then Kushilevitz did it. If you do not have inputs, then it is coin tossing. That is easy. right? Alice can tell the coin tossing outcome to Bob because they are semi-honest. Okay.
For the case that both parties get the same output.
Yes, Alice can toss and give it the answer to Bob.
Generalize it to different outputs. Does the equivalence to geometry disappear?
No. It stays. And there are ways to do this. We have our paper does not talk about it.
So what was the characterization when it's possible and when it's not, right?
Yes, I will give that. So I want to explain this using an example. I want to remind everyone what Kushilevitz characterization was. I will use the famous example of auctions, where Alice can bid either 1 or 3, Bob can either bid 2 or 4, and we want to compute the winning bid. If the bid is 1 and 2, then the winning bid is 2. If it is 3 and 2, the winning bid is 3. If Bob bids 4, the answer is 4. So you do not need to remember the labels. All you need to remember are the colors. Okay, not even the values. Okay. So let's see what's going on. If I know that the output is 4, the winning bid is 4, then I know for sure Bob's input is 4. If it is not, then I know Bob did not bid 4. So Bob can just announce whether he wants to bid 4 or not. Is this clear? This is a secure information to reveal. Condition on the fact that Bob is not bidding 4, the output reveals Alice's bid. So now Alice can reveal whether she is bidding 1 or 3. This is a secure protocol for auctions. This is identical to Dutch auction, where you count down from top and people raise their hands whenever they agree to bid that price. Is this clear? It's counting down. Okay, everyone is comfortable? The question is, why can't Alice speak first? What happens if Alice speaks first? So let's think Alice reveals whether she wants to bid 1 or 3. That is, her input is lower row or the upper row. In that case, observe that if Bob had decided to bid 4, he will figure out Alice's bid, right? If the bid is 4 for Bob, he should not have figured out whether Alice wants to bid 1 or 3. So this protocol is insecure. What is now the summary? We cannot split monochromatic regions. Monochromatic regions have to stay together for security. Okay, so here is Kushilevitz characterization. If you can take a matrix and decompose it such that it is monochromatic region preserving, that is, it is secure, and at the end of the protocol, you have monochromatic rectangles. This is a property of information theoretic protocols, that whenever you end the protocol, you must have rectangles. Yes.
So the coloring the matrix just based on the output.
Yes. So yeah, this is just like coloring. Color 4 was blue. Okay. So there are examples of functions that cannot be decomposed as such. Although everything is a rectangle here, Alice cannot break this or break this, so that she cannot speak, and so likewise. Here is a much more fundamental problem. There is a region of monochromatic color that is not even a rectangle. No way there can be a secure. Now, what about functions with randomized output? So the problem is this approach, we could not see how to extend it to the randomized approach. So the strategy we employed was the following. First of all, we had to realize that we are not Kushilevitz, we are computationally bounded. We cannot come up with a conjecture and try to verify it. That's how Kushilevitz did. He conjectured there is a technique of how secure protocols proceeds, and he verified that that's the only way it can work. We did not have any such conjecture. So we wound back time to pre-1989. Okay, and we need a new perspective to start and recover Kushilevitz result. And let me tell you what is the key perspective that we had. So let me introduce our framework. First of all, we assume that Alice and Bob are picking their inputs, private inputs, uniformly at random and independent of each other. For perfect security, this does not matter. Okay. Suppose the protocol has evolved to a partial transcript tau, and Alice is the one who is supposed to send the next message. She can either extend it to tau L or tau R, indicating whether the protocol should evolve towards left or towards right. This is one bit message that Alice can send. Now, since Alice is sending a message here, Markov constraint says that Alice's message cannot reveal any additional information about Bob's input. Let's be very precise. Bob might have revealed some information about his input prior to reaching here. But Alice's one bit cannot add any other information to Bob's what we know about Bob's private inputs. So let us define condition on this transcript tau. What is the marginal distribution of Bob's inputs? Let's call it rho tau. And here we have rho tau L and rho tau R. So what can we conclude? This must be identical to this because Alice cannot reveal any additional information. And this must be equal to this. So we say that these two partial transcripts are siblings because they have the same Bob marginal distributions. Okay. Alice can reveal input about her input, but no information about Bob's input. Okay. So we'll call these kind of nodes siblings. I want to emphasize one thing here. Markov's law is absolute. There is no finagling around it, okay? There is no statistical version of Markov's law. Is that clear? Is it okay? There is no statistical version. It is absolute and perfect. It's a law of nature. So this is where we decided to start. We do not know how the protocol is going to start from top and proceed. So we decided to go at the bottom because we know that the output definitely will be either 3, 2, or 4. We know that for sure. If the output is 3, we know that Alice's input must be the top row and Bob's input must be the left column. So these indicate the marginal distributions. If the output is 2, we know for sure Alice's input is lower row and Bob's input must be the left column. If the output is 4, Bob's input must be the right column. And by security, both of these inputs must be equally likely for Alice. Any doubts, any questions at this point? Okay. This was our starting point because this is what we know for sure, right? At the end of the protocol, we need to find out the output of the protocol. Make sense? Okay. Look, these two are siblings. Bob marginal distributions are same. So Alice could merge them. And they can merge in any arbitrary lambda 1 minus lambda ratio. I'm just writing down the half-half ratio, okay? Okay, so this was S0. This is S1. There are no more siblings. Now these two are siblings. They can be put together by Bob because Alice marginal distributions are identical. Okay? Make sense? We have recovered Kushilevitz protocol. And thankfully, this approach extends to randomized. Okay? So one thing I have not told you is we are bonding to siblings, right? I've not told you whether it is secure or not. We prove that it is secure. So that is a new perspective on how security manifests. A secure protocol is one in which the leaves or at the end of the protocol is secure. And every internal node of the transcript must respect the Markov constraint. That is it. Yes. Yeah, monochromatic and the ratios must match. It must be uniform distribution over all. It's a very good question. Okay, let's stare at this definition. Where does security manifest? Only in the base case. This geometric action is independent of security notion. So if you want to substitute semi-honest security by differentially private secure protocols, just change the base case. This remains the same. So it's a unified perspective on how security manifests. Okay, there is another insight that these points can be geometrically embedded. Let me be very frank. The difficulty was in finding one such thing. But now that we have found one, I do not think that is the real challenge. There are many more embeddings that we have found after that. So that is not the fact. Interesting part. Interesting part is that it is geometrically encodable. What I mean by this is that if you take 2 points and encode it in lambda 1 minus lambda, then the corresponding point falls at exactly that point on a geometry. So here is a strategy. We start our geometric embedding will look like this. We'll have marginal distributions of Alice and Bob and the function encoding. And we can combine two things. If A equal to A prime or B equal to B prime, we start with base case and keep building these. Our target query point is uniform distribution over X, uniform distribution Y, and encoding of the function F. And there is a B-bit protocol. If the query point lies in this set, you can recover the protocol from the parse tree. And if the query point does not lie in the set, then there is no perfectly secure protocol. That's it. That's the high level overview. Okay. Any questions? Yes.
The dimension will depend on the range of
size of input domain of X, size of input domain of Y, and size of input domain of Z. Typically in this research, X, size of X, size of Y, size of Z is taken as constants. Yes.
With the leaf nodes?
Leaf node is, we know the output, right? The task.
For all the support,
yeah, every output defines one point in SC. Okay. Should I move it?
Yeah. And or you set A and B to be the marginal condition of the output.
It's for perfect security, it is unique, right? So I know that both you were equally likely. At the end, if output theta is 2 times more likely for input 1 than this, then the ratio will be 2/3.
No, I'm talking about the leaf nodes.
Yeah, that's what I said. The marginal distribution will be 2/3, 1/3. If one output is more likely, twice more likely for one input than the other. Okay. Have you seen such a connection earlier between such various disparate sciences? Yes. This connection that was established with distributed computing, with topology, they established a connection using which we were able to bring all the fancy techniques from topology and bring to bear on distributed computing problems. Okay. We can do the same thing in our case, but the most exciting part is the math part in our case is not known. It is motivating new research. Okay, so let me quickly jump over these parts. This was a randomized example. Let me quickly go to the conclusions part. Okay, so I told you this question about whether something stabilizes or not. Very recently, we found that there is a set of size 5. That is, there are 5 outputs. And Alice and Bob have 1-bit input. In this case, the sequence does not stabilize. So there is a function such that there is no perfect secure protocol. It can only have statistical secure protocols. Okay. And this result, bounded number, any bounded number. So there exists a function F. Pick any B. If you have a B-bit protocol, it will be X minus B in security. So this actually falsifies a widely believed folklore. It was widely believed that the communication complexity should depend on just the input-output domain size, and the complexity of the computing a function could be contained locally to parties. just like communication complexity case. However, this was also true for deterministic functions. However, it is false for randomized functions. And our example is optimal because if you have 4 outputs, any function with 4 outputs, it has at most 4-bit protocol. We can show that. Okay, 5 is the optimal number. Okay. The other thing was, it was conjectured that if you have a statistically secure protocol, then you can error correct it into a perfectly secure one. Not anymore. This function does not has only statistical secure protocol.
The output is real value, so it's a protocol that computes like a.
It's a distribution over 5 outputs.
Okay.
So you sample from this. If I have 0, 0, so F00 will be a distribution over 5 outputs, and we sample according to that.
So in your geometric embedding, you have a dimension for each one, each number, 5 times every possible.
X minus y, y minus y, and z.
Okay, each one of them gets a dimension, and you like need to put them together in all of these different dimensions. And sometimes, if an output is not supported over everything, then you should just have a 0 weight or something like.
There is the encoding is tricky. Okay, I will not go into that. But the point is, it's not for anything fancy.
Sure.
Okay. I do not consider it fancy. It was very difficult to come up for the first time. Okay.
Is it crucial that it's real? Can you replace it with rational number?
Oh, very good question. The counterexample that we have has denominator 35, for example.
So no irrational numbers.
No. You can consider rationals. Very good question. You help me sell this paper better. Okay. So if this does not stabilize, can we prove that it converges to some limit set in Hausdorff sets? Okay, does it limit? There is a limit set. If there is a limit set, can we compute it? And our conjecture is yes, yes to both of them. Okay. The interesting part is that solving this conjecture actually needs you to solve equations of this form. Okay. Linear inequalities, where these numbers are not real numbers, they are convex shapes. Okay, and greater than equal to, one shape being greater than equal to another means that this contains the other. And max means this contains both this and this. Okay, and if you can find the smallest solution, x1, x2, x3, that is a solution to such a system, then you would have come up with the limit set. Okay. So as you can see, we are doing algebra using over the polyhedral semi-ring with the containment inequalities. Reminds you of something very famous, something very really cool nowadays, tropical algebra, where they have max plus algebra instead of plus multiplication algebra. Okay. So if we are able to use tropical algebra to resolve this problem, so I think this confluence of MPC with tropical algebra could be called MPC in the tropics. And that will, I think once we resolve this, it will give me a very warm feeling.
At the conference and the places in the tropics.
I think that's what they have been doing. However, the last algebraic geometry workshop that I mentioned was at a very cold place. Okay, with that, I would like to conclude my talk. Again, thanks to my co-authors. And like without them, this work would not have been possible. They brought great.
Yes, you can take further questions.
So if a functionality cannot be implemented with statistical, can be broken with.
Oh, this is a very good question. If there is no statistical secure protocol, can we show that it can be broken by constant probability? Actually, we can show that.
What's the constant?
For every function, it will depend how close it is to the ideal shape. The closer it is, the lesser insecure it is. If it falls inside, zero insecure. If it is near the shape that I was talking about, the query point here, If it is near, then it is less insecure. If it is far, it will be very insecure.
So I'm not trying to understand the question. The question was about statistical security or?
Yeah, so if a query point is not in the set, how insecure is it?
Okay.
It is at least sort of a distance notion from a set. The closer it is, less insecure. The farther it is, more insecure. You can prove this. I'm just lazy to write this one down. By the way.
So you're saying this can give you results about statistical versus perfect security?
Yeah. Again, all I need to do is change the base case. Nothing changes.
Can you raise like oracles? Perfect oracles?
I have no clue how to do these things for oracles. I do not know. Very good question. Like I would like to understand, for example, OT complexity of a function, then I can give them OT oracles, right? I have to change the geometric complexity so that you pay $1 every time you use an oracle. If I can come up with a geometric action for that, then we are done.
So say 3 parties with secure point-to-point channels, all hell breaks loose, right?
Yes, I have to sit down and think about that problem. My student has given me counterexamples to my lectures, so yes.
So you mentioned earlier connection to characterization. So what if you have connections to other stuff like approximate characterization?
So let me be very frank. For 1 year, we tried to prove it. My students did not believe in me, and they were trying to disprove it. Okay. So while we were trying to prove it, we were trying all these techniques on Helly number, Helly number, and Redon for these sets, and we were trying to show that there is some nice properties for them. And yes, there will be open problems because they do not stabilize. Right?
So the upshot is that you don't know?
I don't know the answer. And because the shapes might not stabilize, which is good, right? Like I would have otherwise written only one paper. Now I can write more if possible. But though I really am very sad that it does not stabilize, because otherwise it would have been a really beautiful property. So I really am disappointed with that result.
Okay, great, amazing, really interesting. We can take further questions offline. Thanks, Maji.